In the Bohr model of the hydrogen atom, the one electron of hydrogen is in orbit around the nucleus at a certain distance r. So in the Bohr model, the electron is in orbit. In the quantum mechanics version of the hydrogen atom, we don't know exactly where the electron is, but we can say with high probability that the electron is in an orbital. And an orbital is the region of space where the electron is most likely to be found. So for hydrogen, imagine a sphere, so a three-dimensional volume, a sphere around the nucleus. And somewhere in that region of space, somewhere in that sphere, we're most likely to find the one electron of hydrogen. And so we have these two competing visions, right? So the Bohr model is classical mechanics, right? The electron orbits the nucleus like the planets around the sun. But quantum mechanics says we don't know exactly where that electron is. And the Bohr model turns out to be incorrect. And quantum mechanics has proven to be the best way to explain electrons in orbitals. And we can describe those electrons in orbitals using the four quantum numbers. And so let's look at the first quantum number here. So this is called the principal quantum number, and the principal quantum number is symbolized by n. So n is a positive integer, so n could be equal to 1, 2, 3, and so on. It indicates the main energy level occupied by the electron. So this tells us the main energy level, and you might hear this referred to as a shell sometimes. So we could say what kind of shell the electron is in. As n increases, the average distance of the electron from the nucleus increases, and therefore so does the energy. So for example, if this was our nucleus right here, and let's talk about n is equal to 1. So for n is equal to 1, let's say the average distance from the nucleus is right about here. Let's compare that with n is equal to 2. N is equal to 2 means a higher energy level, so on average, the electron is further away from the nucleus and has a higher energy associated with it. So that's the idea of the principal quantum number. You're thinking about energy levels or shells, and you're also thinking about average distance from the nucleus. All right, our second quantum number is called the angular momentum quantum number. So the angular momentum quantum number is symbolized by L, and L indicates the shape of the orbital. So this will tell us the shape of the orbital. Values for L are dependent on n. So the values for L go from 0 all the way up to n minus 1. So it could be 0, 1, 2, or however values there are up to n minus 1. For example, let's talk about the first main energy level, or the first shell. So n is equal to 1. There's only one possible value you could get for the angular momentum quantum number L. N minus 1 is equal to 0. So that's the only possible value, the only allowed value of L. When L is equal to 0, we call this an s orbital. So this is referring to an s orbital. And the shape of an s orbital is a sphere. So we've already talked about that with the hydrogen atom. So just imagine this as being a sphere, right? So a three-dimensional volume here. So the angular momentum quantum number L, since L is equal to 0, that corresponds to an s orbital. So we know that we're talking about an s orbital here, which is shaped like a sphere. So the electron is most likely to be found somewhere in that sphere. Let's do the next shell. So n is equal to 2. So if n is equal to 2, what are the allowed values for L? So L goes 0, 1, and so on, all the way up to n minus 1. So L is equal to 0, and then n minus 1 would be equal to 1. So we have two possible values for L. L could be equal to 0, and L could be equal to 1. Notice that the number of allowed values for L, right, is equal to n. So for example, if n is equal to 1, we have one allowed value. If n is equal to 2, we have two allowed values. All right, we've already talked about what L is equal to 0, what that means, right? So L is equal to 0 means an s orbital shaped like a sphere. But now, in the second main energy level, right, or the second shell, we have another value for L. So L is equal to 1. And when L is equal to 1, we're talking about a p orbital. So L is equal to 1 means a p orbital. And the shape of a p orbital is a little bit strange, so I'll attempt to sketch it in here. So you might hear several different terms for this. So imagine this is a volume, right? So this is a three-dimensional region in here. So you could call these dumbbell-shaped or bow tie, whatever makes the most sense to you. But this is the orbital. This is the region of space where the electron is most likely to be found if it's found in a p orbital here. Sometimes you'll hear these called subshells, right? So if n is equal to 2, if we call this a shell, right? If we call this a shell, then we would call these subshells. Right, so these are subshells here, and again we're talking about orbitals. L is equal to 0 is an s orbital, L is equal to 1 is a p orbital. Let's look at the next quantum number. So let's get some more space down here. So this is the magnetic quantum number, symbolized by m sub L here. So m sub L indicates the orientation of an orbital around the nucleus. So this tells us the orientation of that orbital. And the values for ml depend on L. So ml is equal to any integral value that goes from negative L to positive L. All right, so that sounds a little bit confusing. Let's go ahead and do the example of L is equal to 0. Right, so L is equal to 0 up here. So let's go ahead and write that down here. If L is equal to 0, what are the allowed values for ml? There's only one, right? There's only one. The only possible value we could have here is 0. So when L is equal to 0, let me use a different color here. So if L is equal to 0, we know we're talking about an s orbital, right? When L is equal to 0, we're talking about an s orbital, which is shaped like a sphere. And if you think about that, we have only one allowed value for the magnetic quantum number. That tells us the orientation. So there's only one orientation for that orbital around the nucleus. And that makes sense because a sphere has only one possible orientation. So if you think about this as being an XYZ axis, excuse me. And if this is a sphere, there's only one way to orient that sphere in space. And so that's the idea of the magnetic quantum number. All right, let's do the same thing for L is equal to 1. All right, so let's look at that now. So if we're considering L is equal to 1, let me use a different color here. So L is equal to 1. Let's write that down here. If L is equal to 1, what are the allowed values for the magnetic quantum number? So ml is equal to, this goes from negative L to positive L. So any integral value from negative L to positive L. Well, negative L would be negative 1. So let's go ahead and write this in here so we can have negative 1, 0, and positive 1. So we have three possible values, right? So when L is equal to 1, we have three possible values for the magnetic quantum number. So 1, 2, and 3. The magnetic quantum number tells us the orientations, right? So the possible orientations of the orbital or orbitals around the nucleus here. So we have three values for the magnetic quantum number. That means we get three different orientations. And we already said that when L is equal to 1, we're talking about a p orbital, and a p orbital is shaped like a dumbbell here. So we have three possible orientations for a dumbbell shape, right? So if we went ahead and put some mark these axes here, let's just say this is x-axis, y-axis, and the z-axis here. So we could put a dumbbell on the x-axis like that. So again, imagine this as being a volume. This would be a p orbital. We'd call this a px orbital, right? It's a p orbital and it's on the x-axis here. So we have two more orientations, right? So we could put, again, if this is x, this is y, and this is z, we could put a dumbbell, right? We could put a dumbbell here on the y-axis. So there's our second possible orientation. And then finally, if this is x, this is y, and this is z, of course we could put a dumbbell on the z-axis like that. So this would be a pz orbital. So we could write a pz orbital here, and then this one right here would be a py orbital. So we have three orbitals. We have three p orbitals here. All right, so one for each axis. All right, let's go to the last quantum number. So the last quantum number is the spin quantum number. So the spin quantum number is m sub s here. And so when it says spin, I'm going to put this in quotations. Like this seems to imply that an electron is spinning on an axis. So that's not really what's happening, but let me just go ahead and draw that in here. So I could have an electron. Let me draw two different versions here. So I could have an electron spin like a top, if you will, this way, or I could have an electron spin around that axis going this way. And again, this is not actually what's happening in reality. The electrons don't really spin on an axis like a top, but it does help me to think about the fact that we have two possible values for the spin quantum number. So you could spin one way, so we could say the spin quantum number is equal to positive 1/2. So usually you hear that called spin up. So spin up, and we'll symbolize this with an arrow going up in later videos here. And then the other possible value for the spin quantum number, so the spin quantum number is equal to negative 1/2. So you usually hear that referred to as spin down, and you could put an arrow going down. So again, electrons aren't really spinning in a physical sense like this, but again, if you think about two possible ways for an electron to spin, then you get these two possible spin quantum numbers. So positive 1/2 or negative 1/2. So those are the four quantum numbers, and we're going to use those to again think about electrons in orbitals.